will be better. Okay, so shall I start?
Yes, please, please.
Okay, so welcome everyone. I'm very happy to give this seminar today. In a moment you will understand why. This is very special occasion for me. So thank you, Robert, for organizing this seminar and giving me opportunity to talk for people from Los Alamos. This is again very special, and why you will notice in a moment. The talk is about computer modeling. It should be computational. I'm sorry for the title. I'll tell you later why the change was made. But anyway, computational modeling with single prompts. This is very modern topic, and actually it's very hard to give this talk without introducing myself. So the reason I will be talking a little bit about myself and why I'm here is that actually today everyone can give a talk about prompting because it's so easy. And but the message I want to tell you about today is that we are witnessing revolution. And let me now go on. Okay, so my journey in physics began when I came to physics department here, where I am here today, and I was always programmer. I was always programming. I came with the knowledge how to write a C++ program, how to write assembler code, and so on, because it was really long time ago. Now, when I came to the institute, I was interested in computer graphics, in programming in general, but I didn't know anything about simulations. Then I came to one of the professors in the institute, to his room, and he told me about some books that are interesting, and one of them was the book of David Potter. This is Polish version of the book. Obviously, you can find it in the English version as well. And this is about computational methods in physics. And yeah, the book is basically about many topics, not only about the particular one that attracted me. What attracted me were those pictures. When I saw this splashing of a liquid droplet going into a deep tank, then I noticed that this is really attracting me, and I wanted to basically repeat it. I wanted to simulate it. And in my head, I had this feeling that I wanted to see that animated. And the thing is that these pictures in the book were reproduced from the famous work of Harlow and Shannon. That was 67 paper. And the method that was developed, that was used in the paper to simulate the splashing droplets, it was the marker and cell method developed at Los Alamos T4 group of Harlow and Welch. And I was digging in the literature. I knew nothing about Navier-Stokes. I knew nothing about simulating stuff. I was, the first, second year, no, it was first year. I was a first year physics student, but I was digging a lot in here and there. I was asking professors about to support, and then I found that what I need is a special report. That was a way that Los Alamos was distributing scientific achievements, not only by the papers, but also by the reports. And I found it hard to find the reports because that was a time when internet was not that developed as today. But I was lucky because at the time I was looking for it, I don't know what was that. Maybe you know more. But there was a moment when Los Alamos has opened the repository of reports to access to everyone in the internet. I don't know the specific year, but then I found this Mac report, the Mac method. So this changed a lot because when I saw this report, I noticed what people have done there. And what they did was a fantastic work on that. In a way, it was very pedagogical. It was very good for student of the first year because I was programmer. Remember, I knew how to program. I was not afraid about writing stuff, and I was really like a coder, you know, doing every day I was doing programming because that was my like. So I didn't. I was not born with mouse, more like with a keyboard. But anyway, the MAC method is a method of solving Navier-Stokes equation with a free surface. So this particular method gives you solution to incompressible Navier-Stokes equations with particles that are showing where the fluid is going. And it is not simple, but it was provided in this way. So what Harlow and Shannon and people, Harlow and Welch have done in this report, they provided a full computational code for solving Navier-Stokes. So what you see on the left-hand side, there are some boundary conditions, there are some discrete operators for partial differential equations, for pressure field. On the right-hand side, you have some what is that? This is a reflux cell. So this is a procedure to reflux the cells from being fluid to part and so on and so on. I understand everything in this code. And when I saw why, because I was studying almost a year, just by looking on the code, I was learning how the solution was made. And this is like many, many pages of this code in the report. But why I'm showing that? Because then I spent 12 months writing the code in C++. And my message today is that that was the, okay, it was 15 years ago, okay? Never ever anymore. This is the end of this kind of study. No first year student will sit down and write code like that. I'm not judging it's good or bad. I cannot do that. But because I was programming a lot, and what I'm now witnessing is, yeah, I won't be like, it will be not too much to say that this is a paradigm shift. And nobody will write a code as I was doing these years. This is like rewriting a book by, you know, by hand. It's not bad. I mean, one can do it, and maybe there will be people who will do that, but nobody will devote such like I was doing by that time. And but of course, there will be still people like I was at the time. You know, I'm not no longer that hardworking as I was as a first year student because I had a lot of time. I had the free afternoons. I didn't have family to take care of and so on. But there still will be people who have this time. So we are not lost because they will spend 12 months on something more sophisticated, on something more complex. So don't worry, this is not bad. Just we are witnessing the change. Now, this is the result of the code. So I'm not the author of the algorithm. I was rewriting the code. Yes, I was by doing that. I was learning. I had to implement it, and so on and so on. But this is a first-year student result. This is free surface flow simulated in many different cases. The splash of liquid drop was in the title page, so you can now you know what was why did I show the splashing droplet. Here are different cases. Now, okay, so that was the introduction. That's why I'm here, okay? That's why I'm here, okay? Now, today, now I'm still working with CFD. I became a CFD guy, so doing computational fluid dynamics in porous medium with some statistical physics background and so on. We are studying tortuosity, permeability. This is where my research is going on. This is an exemplary code from my lab. This is actually written by myself. This is a lattice-Boltzmann implementation. So I was, by the time this 15 or even 20 years already, I was programming a lot. Also CFD solvers. So this is also C++ code, but I'm not only using C++, also different ones. But anyway, so this is a kind of result that is people from CFD world will be familiar with. This is a flow over a car shape from our lab. Now we are also using finite volume. This is open foam and so on and so on. This is porous medium in 3D with the fluid flow going through for two different Reynolds numbers. Okay, that's where I'm here today. I'm doing research in that stuff, but I became interested in programming with AI. because this is a fantastic tool and it's changing the way we are working. Okay, you know, if you ask me if I'm that, how to say, optimistic and that positive about AI, I said fantastic is maybe in a bad word. It's fantastic in a way it's working. I don't know how to judge the change we are witnessing. This we can discuss maybe later. Now I'm doing this programming for many, many years. I started with assembler, C++, so I'm programmer. That's what I want to tell you, because if I'm not programmer, then it won't be justified that I'm saying what I say, and I will say a lot today. I'm teaching programming and I have a book on simulations in physics as well as C++ combinations. This is a book for C++ learners. But then 2025, which is actually wrong, it should be 2024 even, but anyway, 2025, there is a boom, there is a change, and the change is because of DeepSeek. Why DeepSeek? Why not ChatGPT? Why not Claude? So DeepSeek is a Chinese company that has presented, you probably heard about it from news. And this is what we all heard. DeepSeek has appeared as a tiny, well developed, quick and cheap in a way it was developed. So not very, so these people didn't really put a lot of money into development of DeepSeek. But what they did two things. One, they opened the DeepSeek as an open source model. That means one can see exactly what is inside, and one can control it a little bit better, and also one can download. That's how they started. One could download it locally and work in the computer without access to internet. But they also did something more. They introduced so-called deep thinking. That's why they call it DeepSeek, and that was a change. When this appeared, and I was like, up to this time, I was like, okay, ChatGPT, yeah, please write me fairy tale about something. Do this. I was playing a bit, but just to catch up, okay, just to be in the right time, in the right place, not to basically ignore it. I anyway ignored a lot because that was developing for many years already. This is not like popped up from nothing. Yeah, but then when DeepSeek appeared, I've seen some people telling that this is much, much better. Try it, try to ask him for some program, maybe to see how it is programming for you. But you know, people were saying that models are hallucinating. Models are giving you the wrong answers. They are doing some like they miss some concrete knowledge. Then they fill it up with something rubbish. They hallucinate papers. So how they can program? And then I tried it, and come on, this is crazy. Okay, my first day with DeepSeek. Okay, I like to tell stories, so I will tell you a story. My first day with DeepSeek was that I said, okay, I'm writing LBM software for many, many years. Like I know how to program it, I know what is the algorithm. I mean, if this is a computational, like a neural network having this knowledge of LBM, then why don't we ask this network to provide the program? Then I wrote a very simple prompt. Okay, this is already a prompt. So for people who are not very familiar with it, but everyone already is probably, but with chats, you basically put some instructions. And you don't have to put it in C++ or assembler. You can put it in the natural language. And this is what I did. Originally I wrote it in Polish, so later on you will see Polish. Don't worry about it. You can write it in English. If you copy and paste this to chat, you will get basically very similar answer. Similar, not the same. So the prompt here was write a JavaScript program that simulates Poisson flow. You know, I know already what JavaScript is. I know what Poisson flow is. One has to know to write prompt like that. So the knowledge is still needed. using LBM method and present the results in the form of velocity field with white where the velocity is highest and black where the velocity is 0. This is like, talking to student. Please do me this and that, but remember about to make the color like this and so on. So you have to basically point out some, and now imagine the like a pins. You are putting a pin. One pin is Poisson flow. It has to be Poisson flow. The other pin is it has to be LBM. The other is it has to be written in JavaScript. The other is that I know the background is white. Yes, all the other that is not set has to be filled out by the network. So now it is up to you what is the abstract level of what you are asking for. Because if you ask for like specific algorithm and you write down the step by step how LBM is working, this is wonderful. The language model will know how to implement it, and by having those points, it will not have to guess. Here, I didn't put any detail on LBM. What I did, I said implement LBM. And so this language model has to take LBM from somewhere, from the knowledge it has. And now what one could say is, okay, so what language model will do? It will go to the website, copy the code and provide it to me because I was asking for a... This is not true because the language model is a very complex neural network that has a knowledge from different perspectives. Of course, it will copy from the knowledge it has. But this is exactly what we are doing by doing something like that by ourselves. But let me not be the advocate of the devil, but continue the talk because this is a very deep problem and very deep discussion that may come later. Now, so the DeepSeek has introduced this deep thinking. Now let me show you this how it looks like in reality. In like, yeah, I'm sorry, I have to open it in another, yeah, in another. That was very smooth. And okay, let me open this in another. Here, and I have to open this with that. Okay. So let me now open my first chat. Yeah, this is the one of the first. I was just playing with DeepSeek. It was a long time ago. When I wrote this prompt, so I'm sorry this is in Polish, but I provided you on the slide exactly the same in English, so you can do the same. By the way, I wrote in Polish, and the language model started thinking in English, which is quite funny for me. But yeah, okay. Then sometimes it is even thinking in Polish. But anyway, if any one of you has implemented LBM, you will recognize that this deep thinking process is actually thinking about how to implement it. So it's outlining the whole procedure. Like, let me outline the steps. First, parameters. Define the grid size, relaxation time, gravity, so how to force the flow in the Poisson flow, constants, omega, by grid setup, initialization, main loop. He's saying that this is a streaming and collision process because the LBM is basically kind of like a mesoscale model in which you are looking for the distribution function instead of velocity. So you have to stream and collide them, yeah? And so on, and writing an equation for the for propagation of distribution function. It's mentioning Guo force, which is interesting because I didn't mention it, but this is a model for the force term in LBM, and so on and so on. This is very long. You cannot really go into much of the details because you will be lost. It's like a very good student thinking of how to solve the problem provided. Then snippets of the code in JavaScript and so on and so on, and then voila, we are getting a code. The code is there. The code is basically an implementation of LBM. It's very standard. There is nothing else. Okay, so when I saw this, okay, I will run it. Ta-dam! This is the velocity field in Poisson flow. I just run it by one click. And I have a Poisson flow. What is black is zero velocity. What is white is a velocity, the maximum velocity. Okay, I didn't really make a sophisticated analysis of whether this is Poisson flow or not. By eye, I can recognize it is. By my knowledge and experience, I can recognize this is actually LBM, and it is implemented in a way that we are implementing it in our lab and so on. But let me continue because the story is much more deep. Now let's go into like adding something. I was playing, what I was doing exactly the same like everyone is doing. Okay, so I have something like a code. Now, okay, so chat, please add some particles that are flowing in the flow or on top of the velocity. So it basically added procedure like that, and you can see, and the obstacle. So this is an obstacle in the middle. By the way, it's not seen, but this is LBM text written, and then there is a flow over it. You already can recognize hydrodynamics from here. You cannot see particles flowing, but later on I can show you if you are interested, but let me continue because I have much more interesting stuff going on. Then I asked, okay, so why don't you calculate tortuosity for me? Because this is a very simple thing to calculate. If you have velocity field and you have particles going on, then you compute the length of the path of a particle and you average all the lengths that you have in the system, then you get tortuosity. And for this particular flow, tortuosity is 105. Okay, never mind what is tortuosity of a flow over an obstacle, because that's of course the porous medium stuff, the tortuosity. But anyway, I was like playing with the thing. Then I said, okay, so if it can compute tortuosity, by the way, this took me to not, I mean, it took me like, I know, writing a prompt was 5 minutes because I was has to think of how to, of course, plan it to make it working. Then few minutes to add particles and one single and compute tortuosity using this definition. Enter. Then I get that. I said, wow, when I was PhD student, because when I did this splashing droplet, I was master. That was my master student project. Then I did PhD in porous medium. But when I was starting, I was learning LBM for, believe me, 6 months. I don't know, maybe I'm that stupid, but it was really very hard for me to follow that simple method because it was awkward. Why don't you compute velocities and why don't you discretize Navier-Stokes in some way, but you are using some awkward distribution functions and you get velocities at the end and this and that. Then I was learning because there was no one to help me. Yeah, now you have it for free. I mean, you can write it down like that and you get it. You get the code. Of course, okay, let's discuss later what you lose or you gain. But anyway, you have it. Now, then I thought, okay, in 2008, I have this paper. This is from me, my supervisor from Max Planck Institute in Bremen, and my supervisor from Wrocław. This is one of the most important paper from my PhD, published in 2008. And what we studied here was tortuosity-porosity relation in porous medium flow. Now I have to explain you a little bit about this particular plot. So I said, okay, so why don't I try to work with LLM, to work with DeepSeek, and try to repeat what I did for PhD? Because now, okay, I have a code, I have tortuosity, so why don't I produce a porous medium of many obstacles and compute tortuosity for like in a function like that? And I said, okay, so what do I need for this? Okay, what is the plot? So on the y-axis, you have tortuosity. The larger value of tortuosity means the flow is more wiggle. It goes on the more like tortuous path. The less number, so 1, is straight flow. Okay, 1, the particle goes from the beginning to the end of the medium on a straight line. When tortuosity is 1.6, it goes like that. Okay, now there is a transition of tortuosity from 1 to, let's say, from 1 to 1.7 or whatever. This goes actually to infinity because of percolation threshold, but with a fraction of pores. If the fraction of pores is 1, this is basically the channel flow without any obstacles. If you are close to 0.45, that means you packed a lot of obstacles and you have percolation threshold, close to percolation threshold. Actually, tortuosity should go to infinity. But this is very hard problem numerically because I solve Navier-Stokes really in the pores of the porous medium. This is a pore scale study. Now, okay, now you understand what is there, more or less, because this is more details on how I averaged it to get these error bars and so on. This is like empirical equation. These are my results, numerical ones, okay? Okay, so that's the paper. Now I said, okay, so this is a prompt to write a program to repeat results from my paper. Now you can, I don't want to go into many details of this particular prompt. I call it tortuosity calculator in GPT. So this is a result of a week of work. I was working a week adding and doing trial and error analysis of how the prompt is producing the code, how the code is behaving, how I can compute something or not, and so on and so on. Because to write a complete program, to compute a plot like this, you need to average over different systems. You need to have, for instance, you have to remove particles that penetrate obstacles. During computation, calculate tortuosity from velocity field. Now, add sliders so that user can change the external force, because I wanted also to study the effect of inertia, for instance. Remove particles that hit obstacles and place them randomly in the flow domain. This is repeating of that, remove particles, but it's more specific because I at some point recognize that he does something awkward with particles. So I have to pin, I have to tell it that this to this chat that make it in this or that way. Now, okay, to compute anything, I need to be able to compute on different systems. Then I had to add a button to randomize the configuration, and so on and so on. So now you see, this is not very specific in LBM terms. This is more specific in the problem to solve terms. So I have the problem of the tortuosity in which I want to have a program to work with, and that was something I had to be really picky on to have it useful, to have some, because I could generate anything with this chat. This was like, I didn't program a line of code, I just wrote that. Now what you see is a single prompt. At that point I recognized that what will be the value in this field, what will be a value for me as a scientist, is not that someone has solved a problem only. What will be, and I see the whole chat and all this deep thinking stuff that is like 100 pages of thinking of process. What is more interesting to me is to have the prompt, the question that was asked to the chat to get the answer, because then I can develop on top of that. Actually, this is a result of multi-prompting. I was like doing trial, error, trial, error, trial, error, and then at some point I said, wow, okay, this produced exactly what I wanted. Then I will show you the program because I have it. The program looks like this. Let me open it. Yeah, it's there. So this, let me make it larger. Okay, this is a fluid flow over obstacles in which I can change external force. Let's not touch it. It has the slider to change porosity, so I can do like 0.93, then it will be like this. And you see tortuosity is 1.0. What happened? One has to be careful because this is numerical work. In numerical work, if you have a large external force and you do not too many obstacles, then the drag is too little and the flow increases speed too much over the Mach number that is acceptable by the LBM. So therefore you need to be careful and you cannot do external force like this. So let me do again. So this is a typical for, so I know from my experience that you cannot do it. Now it can explode again because this is very hard in high Reynolds numbers. One would need to increase the grid and so on, but let me decrease the external force. Now tortuosity is low, 1.0 something, okay? Now let me make porosity like that, but with in a way that it is still flowing, because that's also, so now we have a lower porosity like this, 0.62, and let's wait a little bit. But now you can even recognize tortuosity is 1.21. 1.21 is larger than it was when we had a little bit less of those obstacles. So for higher porosity we had lower tortuosity. Now for lower porosity we have higher tortuosity, which is exactly what we would expect from this plot. Okay? This little amount of, number of those obstacles, this is where there was a dense system with many obstacles, so tortuosity was larger. Of course, the specific values one has to make exactly the size and so on. This was a little bit of tweaking of parameters, because this is also challenge to select parameters that are okay. So this is a result from the paper, from my PhD, and the red dots are the results after tweaking of parameters like the size of the system and so on, that I computed with the code generated by DeepSeek. And now, believe me or not, but this paper, Tortuosity Porosity Relation in Porous Medium, from PRE from 2008, it was 1.5 years of work. I was learning by the time. I was really hard working on the simulations, and it was a lot of effort. Now I did it in 1 week. Of course, I have an experience. I agree, because people say one has an experience, then it goes faster with LLMs and so on. But I cannot agree that 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 we are not witnessing revolution here. Okay, let me go on. Then I said, okay, so maybe we do something new. In what way new? So in my field, people are very often looking for the empirical relations, not even heuristical, or I don't want to categorize, but empirical, in a way that they're observing the how some tortuosity changes with porosity. They try to fit a function. They are looking how this behaves in different class of a system. Then I said, okay, so let me do something very simple. Just ask the LLM to do something, a little bit of change, something that from my experience is okay, maybe not the highest impact factor journal paper, but in 2026 is publishable. Something that I feel like, okay, I could publish it if I have a result like this, but I never did because it was too much of an effort to do it. And I mean, because why one wants to devote a lot of time to write a program to do something such as simple that just one move. So you change this kind of a system. And I changed the system to something like this. Okay, we have those obstacles, but they no longer overlap. Because in the previous one, here, they could overlap. And this is a result for the overlapping. Okay? Then I said, okay, so I do non-overlapping. This has immediate consequences. So for instance, you cannot go to the percolation threshold, because those non-overlapping obstacles, they have some separation distance. Then I got results like that. And then I stopped, because I said, no, it is too simple. How I can publish that? I mean, it was like one sentence I wrote. Then I got the code, I ran it, and I got those results. And then I said, ooh, our life gonna change. Because before, 5 or 10 years ago, if I gave this to a student and he provided me result like this, I would say, okay, let's sit down and write a paper, because this is linear, this is non-linear, it's interesting, and this and that. But now, why? I mean, it is like just another result I can do like that, results with porous medium. That's what I feel, okay? This is my feeling. So I stopped at this. Now this is nice for presentations, and anyway, so you see this linear behavior of non-overlapping obstacles. This basically represents the idea that if you add an obstacle, then tortuosity grows linearly. So all this adding of obstacles gives you the linear increase of tortuosity. Okay, one could create a theory for that, maybe even. For the overlapping, you have this percolation threshold effect, so that should go to the infinity, and so on and so on. And you finish at 0.58, because with this distance that I assumed, I could not go, sorry, lower with the porosity. Now let me stop a little bit with physics for a moment and tell you a little bit more about those chats and language models. So what we have in the market for the moment is not only DeepSeek. We have a GPT with deep thinking. So just you cannot, if you didn't catch up with that, I mean, in the past when DeepSeek has appeared, I tell you that was amazing. Because when DeepSeek appeared, introduced deep thinking, then Chat GPT introduced deep thinking 5 days after, 5 days. They already had it. They didn't show to people. And deep thinking in OpenAI has appeared, really, that was so visible because DeepSeek has introduced that. I'm just asking myself what they already have in the company and they didn't show, but okay. Then they introduced some 303 model. This is already history, even though it has a 1 year. Now we have GPT-5, Claude, Gemini, Grok. In Poland, we have a very nice Bielik. Ernie and Quen, be aware that those Chinese models, they have a very special policy in which you cannot use what they produce as it was yours from yourself. Okay, so be aware. So read the policy when you work with chats. The most safe is OpenAI, obviously. Claude, Gemini is it has a very nice policy as well. Anyway, let me go on, okay? Because that's what are the limitations. I was asking myself, okay, now I can do LBM. Maybe I can go for something more crazy. Where are the limitations? Then I recognize limitations are in my head, because my knowledge does not really allow me to go beyond. It is very hard to ask for something you don't know how to do. Up to this, I knew how to do this tortuosity stuff. It was like normal. I'm working for many years. And then I know from the fluid mechanics and computational fluid dynamics, I'm sorry, I know what is very hard. And then I said, okay, with a little bit of, shaking in my heart, I was like, okay, I will ask if he could give an obstacle and rotate it. And then I got this. It is not perfect. It is still LBM. But look what I got. This is crazy. Okay. This will be crazy when I open it. Okay, no, it's good that I don't. It is good that it works anyway. Okay, let me show it. Okay. Now we have it like we have this. Let me open where is. I don't know which one will be there. I mean, okay, this is one of the versions. Okay, there is many more of them. But anyway, this is really hard numerically. It is not perfect, but what you see is the influence of rotating obstacle, which is off grid, because this is not the grid of LBM is underlying the obstacle, but those obstacles are really accelerating the flow. This is crazy, because I know how hard is that. I would not write it, not in 1 week. I would really need to spend time and devote a lot of effort to that. Then I asked, okay, and I really typed this, what you see in the here as a citation, make it 3D, enter. Then I got generalization of one of the simplest tasks for I'm sorry, I will not open it because it's no, it's there. Yeah? No. Anyway, one of the simplest tasks for a program is because when you do two-dimensional solver in CFD, this is not very sophisticated grid and so on. Very often, generalization to 3D is not that hard. It is very technical. So these charts are perfect on it. They just do it. They do two-dimensional solution to 3D like that. Just I got it and it was working. So later on, if we have time and you ask about it, I can run it for you, so you can see the flow in 3D. It's really fantastic. It looks, and I was amazed that it basically works in the web browser, okay? And I can compute tortuosity. And again, from my experience, few years ago, if someone came to me with tortuosity results for three-dimensional system like that, I would say, okay, it's not maybe the most sophisticated research in the world, but we can publish it. And today, I mean, many people will publish stuff like this. I'm not gonna do that. It's too simple. I mean, you know, everyone can do it. It is there. I mean, this is the time one can gain a lot of publishing a paper by paper, but I don't need that. Yeah, I can really spend more time on one paper and be more happy. But one can do it, and people will do. So be aware that if something is programmed, nobody will program it today. I mean, even Linus Torvalds, the author of Linux, said just 2 months ago that this is the end of development with a normal with a style that we're doing till today. One has to use those things, otherwise we'll be like really in the back. Okay, but one can do different, of course. Now, then I became interested a lot. I mean, I had a vision always that I want to write a book on modeling. But this was very hard because I have so many models in computational physics and not only physics that I wanted to work with that I was always lost. I have a list of models I want to implement in my life. I don't know that I already implemented many of them, dozens. I mean, really like 25 or 30, like LBM, diffusion limited aggregates, diffusion this and that, and so I really like it. Yeah, I like to implement. That was my work. That was where I got and gained a lot. But then I figured out that this single prompt is a value, and I said, okay, now I can work this way and create those prompts, because this prompt is not easy to do. I mean, you have to write it in a way that it will work. And then I submitted to Taylor Francis, so there will be a book. And yeah, this is a small advertisement because you may get the book in 2 months from today. And I think you will like it if you like the idea of single prompts, because it's a full of prompts. Now, to work with prompts, there is a different level of abstraction that you can have. You can either do detailed description of the algorithm, details and formulas. Some elements can be omitted, like I did with the LBM, but also some prompts can take you even more than a week of work. And this was the example of tortuosity calculator, but I also have examples of prompts that in very, very detailed level have to introduce the algorithm and details of the algorithm. And honestly, I tell you that in computational physics, a good prompt could serve as a complete description, like a very clean and complete description of how to implement something, and it would be very valuable part of computational physics papers, because people could take a prompt like that and basically repeat it. And yeah, now I have two examples. Now I don't like to. Yeah, I still have 4 minutes because I have my. Okay, so I have two examples for you. One is the Ising model. I won't go into details of the model here, but I'm showing that because it's a very detailed description of the model that I did. Why did I make such a detailed description of Ising model? This is a standard. Everyone can write it, like, write me a Ising model simulation on the website and blah blah and enter, and you will get it in DeepSeek. Yes, but if you write in this way, then you can change the Hamiltonian. You can change by tweaking some details, like the probability can be not exponential but something else, just by changing in the text here. So there will be still a value of doing that on the much lower level. So this program gives you a code that gives you the phase transition. It works. You can basically create and I even asked to fit Onsager theory, and it works. I got this, yeah. Now I did one prompt that was like a special, something not found in the literature. I said, okay, let's make a ballistic deposition of particles going to the middle. Something like this, that ballistic model. This model do not exist in the literature. It is very simple. You basically have a circle, you shoot to the center. If something hits the central cluster, you get that. Oh, there is a mistake. No, this was basically a program produced by Grok. But anyway, there is a mistake because I have this underlying grid here visible. So the model is wrong in a way, but this is an advantage here because I'm showing you that you can do something awkward, something different, something that you won't find in the internet. Then the book is ready. I already did it. It was like, oh, a lot of work, but I devoted a lot. It was really fantastic work. I have even hydrodynamics, SPH, granular matter with static friction, and so on and so on. Very simple game of life, but there is a lot of surprises in the models because I was very like, the freedom was infinite for me. It's like ocean of possibilities for people like me because then I can implement everything quickly, play with it. So yeah, this is the thing. Now, what beyond single prompts? This is one of the last slides here. So one can do multi-prompting, prompt question multi-prompting. One can inject one prompt into another. One can do a lot of in terms of prompt engineering, which I believe this is the future. There is a MPC, very interesting technology. By the way, my student Shimon is working with that, and he brings me a lot of those ideas that I'm showing here. That you can write a tool like a solver for fluid, and LLM can use it by doing research. Now we also have a very nice, but this I cannot show you. There is not much time to show you the result, but we did with the students. So actually, that was an idea of me and Shimon, but Shimon has implemented, and you have the GitHub, you can download it. You can connect two LLMs that talk to each other and give them roles. And I gave them role. I was just playing with that before this talk. And I cannot give you the answer yet because it's not yet ready. But I asked the one LLM to be professor and one LLM to be PhD student. And I said, and the initial message from professor to the student was, hey, let's write scientific paper. And they started to chat to each other automatically by the code of Shimon. And they produce a paper. That's crazy. Okay, now the latest news. I'm doing modeling classes and I will give on Warsaw the class for students on it. In next year, I also give the full lecture here, the specialized lecture for our students. I go to Interport, to Nantes in France. If anyone will be there, then you can meet, and will have a poster on it. And I will also try to go to Prague. I'm thinking how to submit there and how to find money, because of course this is always something one have to think of. Summary: we are dealing with something new. I would say there is paradigm shift in programming. No longer C++, assembler, Python. We will use natural language. There is a rule. If the model will handle if this is feasible, and if people ask about creativity, there is creativity, and people call it hallucinations. But I can be advocate of the devil. You can ask me. Thank you for your attention. That's it.